Much love. Remain majestic.
Okay, welcome to Sa Majesty Easy World Science channel. Today I will be analyzing aluminium tetraoxosulfate 6. That's it over here, and I've collected a sample, small sample here. Now, what I need in this analysis is I need aqueous ammonia, ammonium hydroxide. Then I need a sodium hydroxide, aqueous dilute solution of it, and this is my barium chloride. I need also dilute hydrochloric acid. Then my test tubes are there. I'm now coming to the camera. You can see here I have my test tube and my test tube rack. So these are the things I needed for the analysis. Then a dropper in case when you're required to add in drops and in excess. Then my glass rod to stir. I have a little beaker, 100 ml beaker, just to pour my sample C or whatever you call it, aluminum sulfate, into it and add the required volume of distilled water. Here is my distilled water. And then we also have blue and red litmus paper to test for the aluminum sulfate solution, to check for hydrolysis. Of course, aluminum sulfate actually will hydrolyze in water to give you an acidic solution, as we will see today, because aluminum sulfate is a salt of a weak base and a strong acid, and therefore when it hydrolyzes in water it will give you an acidic solution, and that is actually turned blue litmus paper red. Okay, so first I will have to add a known sample, a spatula. It's about a spatula full of the aluminum sulfate, approximately. Then you'll be required to add about 10 ml of distilled water. In this case, the volume of water is not your problem. Just add enough that will make it dissolve. Remember, aluminum sulfate is highly soluble, and is also used in making of alums. Of course. If you mix it with potassium sulfate, the molar solution of aluminum sulfate and potassium sulfate gives you potash alum. So I'm stirring well to dissolve. Okay. As you can see, the amount that I've dissolved is enough for the analysis. Now, in the likely question, you'll be told to dissolve the whole of C or whatever alphabet they are using in about 10 cm cube or 5 cm cube of distilled water. You stir well to dissolve. Then next instruction, you'll be told to test the resulting solution with litmus. So over here I'm going to use my litmus, both blue and red litmus paper will be used here. So definitely I told you to have action on blue litmus, because I already know I will not waste time testing with red, because it won't do anything to red. This is blue, partially stained with some acidic solution, but it's still good enough to indicate. So that's the blue litmus. I have to insert it into the solution. You see, it turns blue litmus paper red. So your inference should be, in this experiment I just did now, you say sample C is soluble in water and the solution of sample C is actually acidic. So you see it is acidic, that's why it turned blue litmus paper red. Then the first thing you might be told to do, we will have to test with aqueous ammonia. We collect the first portion and then test with aqueous ammonia. This is my test tube. Remember to wash well, collecting the small sample. This is standing as my first portion. Remember, in exam it might not.
Hi, my name is Cheryl.
And I'm Jennifer.
Guess what? There's a channel called Sa Majesty Easy World Science.
And you know the best part?
It
makes science so easy. Wow.
It makes science easy, simplified, and very, very fun.
Guess what? Rocket science ain't rocket science anymore.
It's now ABC.
Like if you did science your entire life.
Another thing about Sa Majesty Easy World Science channel is that he makes available laboratory equipment and reagents.
Guess the best part? If chemistry has been hard for you, he does tutorials.
And another thing is, when you order for these things, they are high quality and they are also cheap. and affordable for anybody.
If you want to order, just look at the number below the screen.
And don't forget to subscribe and hit the little notification button down below.
Don't forget to share, of course, obviously, there's love in sharing.
Thank you. We'll see you there.
Okay, here is my first portion. Remember, it might not be the first experiment I'm going to carry out on this solution might not be the first one you see on the question paper. If it is in an exam, you follow strictly the instructions given to you by the examiner. So here, I want to add sodium hydroxide in drops and in excess to this first portion, and I want to use my dropper to add in drops and see what happens. So here is the sodium hydroxide. Now to keep it for you to see in the camera, let's notice what happens. You say in drops there is a white gelatinous precipitate, of course. There is a white gelatinous precipitate. You see it's sticky to the walls of the test tube, though the gelatinous nature is not showing well here. So yeah, it's gelatinous, of course. See it's not powdery, so just like it's forming a gel. The gel is clear. Then in excess, you require just to pour this. See, it dissolves in excess. So your observation should be white gelatinous precipitate formed in drops of sodium hydroxide, which dissolves in excess of the reagent, sodium hydroxide. In your inference, since the reagent we used is sodium hydroxide, our inference will now be aluminium ion or zinc ion present, because these are the two ions, the two cations that will form white gelatinous precipitate with sodium hydroxide and dissolve in excess of it. Reason is this: the two are actually amphoteric. They are hydroxides and they are oxides, meaning zinc oxide and aluminium oxide, which is that white precipitate you saw, that's aluminium oxide. They are amphoteric. In the presence of this excess base, they react to form a complex salt. What is here is now sodium tetrahydroxyaluminate 3, and that makes it soluble in excess. That's why zinc and aluminium dissolves in excess sodium hydroxide. Lead also dissolves. Lead also shows us similar reaction, but the difference is this: lead will give you powdery precipitates in the beginning with sodium hydroxide and not gelatinous. But because the precipitate was gelatinous, there is no need of putting lead again. This is scientifically. I don't know if your exam body have noticed this. If it is powdery, you can now suspect in drops. If it is powdery, you can suspect calcium, lead, yeah. But lead will dissolve in excess, but calcium will not dissolve. But if it is gelatinous, you think about zinc or aluminium. So that is it. I've told you what to do in observation. You say white gelatinous precipitate formed in drops, which dissolves in excess to form a clear solution. Your inference, zinc or aluminium present, or zinc or aluminium likely. Now, the next step, we take the second portion and repeat the same process, but this time around using aqueous ammonia and no more sodium hydroxide. So this is my test tube. I have to rinse it with distilled water, put in my sink. Okay, now this is the sample. Initially, I'm collecting the second portion. You'll be told to divide into 3 or 2 portions. Just follow the instructions well. You see, this is my second portion, and here is the sodium this is aqueous ammonia, of course. So I want to add in drops and also add in excess. So I'll gently use this for drop. Okay, see, there is also white gelatinous precipitate in drops of of aqueous ammonia. This is aqueous ammonia, that's ammonium hydroxide, or ammonia aqueous, that's ammonia solution. You see, if you look where it is sticky to the walls of the test tube, and that's why we use the term gelatinous. Then in excess, let's see what happens. You see, if you are not careful, you will report something wrong here. Some will say it's dissolving. No, this thing persists automatically. You compare these two, you see, this one dissolves while this is persisting. So it's not dissolving. If you keep this or filter it, you still see filtrates coming out. So which means aluminium do not dissolve in excess of aqueous ammonia, but dissolves in excess of sodium hydroxide. So if you see well here, you see that precipitate, it is persisting. I poured off some of the liquid and they're here. See, so your observation with aqueous ammonia, you say white gelatinous precipitate formed in drops but persist or insoluble or remained in excess of aqueous ammonia. Your inference now is supposed to be aluminium confirmed. This is enough to confirm anion since we have used sodium hydroxide and it gave us this result, and we have only two ions that behaves this way, gelatinous in drops and dissolves in excess of aqueous ammonia, which are zinc or aluminium. But here it persists. If it were to be zinc, zinc will also dissolve in aqueous ammonia just like it dissolved in aqueous sodium hydroxide. But to stay on the safer side, you might be told to add third portion. You might need third portion to confirm zinc, to confirm aluminium. But if you are told to just divide into two portions, your job using aqueous ammonia and sodium hydroxide, immediately you use aqueous ammonia, you suspect aluminium or zinc. Then when you use ammonia, if you use aqueous sodium hydroxide, you suspect zinc or aluminium. But when you use aqueous ammonia, it confirms which one is there, whether aluminium or zinc is there. But to stay on the safer side, you might be told to carry out the third reaction. On third portion, you might be told to add HCl. That's over here, hydrochloric acid. If I add this hydrochloric acid, there won't be any visible reaction, and that confirms aluminium ion. So there is no visible reaction at all. So that shows it's aluminium. Why? Because aluminium chloride is soluble. So there is no visible reaction. We have detected the cation present on this sample, which is aluminium. So the next is that you might be required in the next portion to add barium chloride followed by excess hydrochloric acid. So I'm rinsing this. So I'm collecting the next portion. It might be third portion or fourth portion, but here is our fourth portion actually. You see it. Then I want to test for the anion present. I've settled the cation. It's obvious that the cation present is aluminium. So here is my barium chloride. Your job is just to add it. There is no need of saying in drops or in excess. Just add. Okay. See, it is forming a white powdery precipitate with barium chloride, and that shows that a sulphate or sulfite or carbonate is present. So this my barium chloride is not as pure as it's supposed, but it's still giving us, I might repeat it again because the powdery precipitate is supposed to be too obvious, although it's showing there. Then you followed by adding excess hydrochloric acid. If you add excess hydrochloric acid, if it persists, you confirm SO42-, that's tetraoxosulfate 6 ion. Now over there, adding the acid. See, it is persisting, it's not dissolving, it remains as it is in the beginning. So this confirms tetraoxosulfate 6 ion. Okay, I want to rerun the test for the sulfate 6 ion, that's tetraoxosulfate 6 ion. I changed the barium chloride, just got a fresh one. So although the one I previously did is also reliable, that's the sample. See the sample there. Okay, so then you just add barium chloride. And if you add barium chloride, there will be white powdery precipitate immediately. See, there's white powdery precipitate. And that's it, the white powdery precipitate. Now, to confirm which of these is present, you are required to add excess of this dilute hydrochloric acid. You add excess dilute hydrochloric acid to it. See, it persists in excess. So this confirms sulfate, tetraoxosulfate 6 ion. If it were to be trioxosulfate 4, it will dissolve to give you a colorless gas with the odor of burning matches. If it were to be trioxocarbonate 4, it will dissolve to give you a colorless, odorless gas which turns lime water milky. So that is it for the analysis of aluminium sulphate actually. Remember, the results we got is first we dissolved it in water and it is highly soluble in water. Our observation is that sample C dissolved in water and we tested the solution with litmus. It turned blue litmus paper red. Our inference was that C is soluble and the solution of C is also acidic. Then we collected a first portion of the aluminium sulphate and tested with aqueous sodium hydroxide in drops. It gave us a white gelatinous precipitate in drops, which in excess dissolves to form a clear solution, which is still over there. So then this is it with sodium hydroxide. Then we tried the same process using aqueous ammonia. It gave us a white gelatinous precipitate in drops, which persists, which is here in excess. And our inference with sodium hydroxide is a zinc or aluminium because it is gelatinous. But if it were to be powdery, you have to add lead. But the only two cations that will give you gelatinous precipitate with sodium hydroxide and dissolve in excess of it should be aluminium or zinc. Then when it persists in aqueous ammonia, it confirms actually aluminium, because if it were to be zinc, zinc will dissolve in aqueous ammonia because zinc is a transition metal. So zinc and aluminium behave similar with sodium hydroxide. Why? Because both are amphoteric. Their hydroxides are amphoteric, but they behave differently with aqueous ammonia. The reason here is because zinc is transition metal while aluminium is not. Therefore, zinc can form complex ion with aqueous ammonia, but aluminium cannot, and that's why aluminium ion do not dissolve in excess of aqueous ammonia. So God bless you and remain majestic. Much love from me to you. You can also book for your private classes with Her Majesty. Remember, your academic success is my topmost priority. I cannot do without you. Remain majestic, of course. Like and share my videos.
Yes, I'm getting the video.
Oh yeah, take the camera closer to the voltmeter.
1.1.
1. That's 1.3 minus. It's more than 1.1, guys.
It's more than 1.1.
It's 1.3 that minus 0.2, right?
Yes, sir. It's 1.1.
Yes, so he has gotten the complete video the cell now. And that's Udan against cell. Imagine. That's great. The salt bridge. Keep quiet.